Hello, welcome back. Hope you had a nice break. Maybe got a snack or two, maybe some tea. I'm enjoying some tea this morning. I'm drinking decaffeinated, I know, kind of weird, but decaffeinated black chai tea, which is very nice in the morning. Although, if you're more of the caffeine type, maybe don't try the decaffeinated version. Go for the caffeinated. Anyway, I really love chai tea. Yeah, any tea drinkers out there? Huh? If there are any tea drinkers, I imagine maybe two people in the room raising their hands. Yeah, for me, I have to imagine that I'm in front of you guys. Otherwise, this feels so random. I'm just sitting here talking to my computer screen. It feels so impersonal and weird. So I kind of have to Zen meditate myself, Zen meditate myself in front of the room, something like that. It kind of works. Yeah, actually, it mostly doesn't work, but yeah, I try. Anyway, hope you're enjoying your morning. Let's get back to work here. Let's see. We've talked about how to figure out the pH and the H3O plus concentration that you get for specific types of acids. So you can have either the strong case or the weak case. What we want to talk about now is something called percent ionization. Whoa, that's a really bad O. Okay, percent ionization. And percent ionization is exactly what it sounds like. We want to know how much a weak acid ionizes. The dinosaurs you hear in the background are just my children. Don't worry. How much does a weak acid ionize? We can define this as percent ionization is equal to the H3O plus concentration, so the amount of hydronium that you form from the acid at equilibrium, divided by the initial HA concentration times 100 is equal to the ionization percent. So if we have, for example, an initial concentration of 0.200 molar HNO2, okay. From this, if we go through the process, we find that the H3O plus concentration is equal to 9.6 times 10 to the minus 3 molar. Okay, that means that our percent ionization here is equal to 9.6 times 10 to the minus 3 divided by 0.200 times 100 gives us, let's see, where are we? 4.8%. Okay. That means that, on average, approximately 5 molecules per 100 molecules are ionizing. Okay, so approximately 5 out of 100 molecules are ionized in solution, which is surprising if you think about it. I usually expect there to be a lot more of the acid existing in the deprotonated form or the dissociated form. So it's always very interesting to me to actually calculate the percent ionization, simply because it gives me a better, more practical understanding of what is actually occurring in terms of the chemistry of the reaction. Now, 5 out of 100 molecules is a really small amount. Okay, it's a really small amount, and the concentration is quite small too. If you look at the initial concentration, right? So these numbers, it's hard to make sense of them, right? You can talk about 9.6 times 10 to the minus 3 molar, but once you put it in terms of percent molecules ionized, it starts to make a little bit more sense inside my mind anyway. It makes a more objective sense. Let's look at a more concentrated solution. So let's do 2.5 molar HNO3, same acid, HNO2. If we look at the H3O plus, that 3 got away from me, H3O plus concentration, that is equal to 0.034 molar. Okay, so let's calculate the percent ionization here. Percent ionization is 0.034 divided by 2.5 times 100 is equal to 1.4%. Okay, so above, with a less concentrated solution, we started out with 0.20 and we went to 2.5, so we we increased it by more than a factor of 10. We see that the percent ionization goes down significantly. Okay, so it's about 1.5 molecules out of 100 are now ionized versus the 5 the 5 that we had before. Don't worry about the dinosaurs in the background. I'm safe. I'm locked in my room. I'm safe. They can't come in here. Okay, this is actually a general trend. So the more concentrated a solution, maybe I should write that differently. The more concentrated a solution, the less ionization that occurs. Oops. I think occurs only has one C, right? No, well, dang it, I don't know. Maybe there's another C in there. This is a word that I always misspell, and it's just, that's the way it's gonna be. I'm never gonna be able to learn it. Okay, so the more concentrated a solution is, the less ionization that occurs. And this is true, this is something that's true for all weak acids. Okay, the more concentrated the solution is, the less percent ionization, or the less ionization occurs per total molecules. Okay, so therefore, the increase in H3O plus concentration is not linear. With an increase in initial acid concentration. Okay, it's not linear for weak acids. I should note. Okay, not linear. The more you go up in concentration, the more H3O plus you will have in solution, to be sure. But the less total percent ionization is occurring. Okay, so less molecules per the total will be ionized, but you sure will end up with more H plus in solution. Okay, so that's percent ionization. Let's see what happens. Chemists are curious creatures, right? Let's see what happens when we start to mix acids together, okay? The first thing a chemist asks when he discovers something new or he finds a new material is he says, okay, what happens when I mix it with something else? And sometimes it's a really cool reaction. Sometimes it's kind of an explosive reaction. Those are the best kind. When you get those nice explosive reactions, that's primo stuff right there, okay? So, of course, the next logical question that any good chemist would ask is, okay, I have strong acids, I have weak acids. What happens when I mix them together? So let's mix a strong and a weak acid. If I have a 0.10 molar for example, HCl solution, and I mix it with a 0.10 molar HCOOH. This was formic acid solution. Okay. Now, in this new solution that we form after we mix, we have 3 sources of H3O+. We have, number 1, the HCl reacting with water to form H3O+ and Cl-. We have the formic acid, HCOOH, reacting with water to form H3O+ and COOH-. Then we have, actually I should write this differently. It's actually HCOO-. Same formula, it just denotes that the H is actually coming off of the other side of the molecule. And then, of course, we have the autoionization, which is H2O plus H2O going to H3O plus and OH-. Okay, the Ka for these 3. Okay, the Ka in this case, this is a strong acid, so the Ka is actually undefined. We just assume that this is a complete dissociation, which means that this is not an equilibrium expression. Therefore, the Ka is undefined. The Ka for formic acid is 1.8 times 10 to the minus 4. Oops. And the Ka for and the Ka for the autoionization of water is 1.0 times 10 to the minus 7. Excuse me. It's Kw, so it's negative 14. My bad. Okay, so there's 3 sources. We want to answer the question of how much H3O there is in this solution. Okay, how much H3O is in solution? As a first estimate, this is a pretty good estimate because the Ka value is small for these other 2 reactions, is we're going to assume that the H3O plus that we get is only the H3O plus from the strong acid. Okay. The dinosaurs are coming. I don't know if you can hear them again. They're trying to get in the door. Oh, you know that scene in Jurassic Park? I think it's the first one. Although it could be Lost World. I don't recall. Anyway, that's one of my favorite movies, by the way, because it came out when I was a kid. And it was kind of one of those movies that you watch and you become so interested and also terrified at the same time of meeting a dinosaur or meeting a velociraptor or a T-Rex somewhere. Even though it's like a complete impossibility, you suddenly get afraid of this. And at the same time, you suddenly get very interested in dinosaurs. Anyway, I love that movie. But there's a scene where the girl is hiding in the kitchen. And there's velociraptors trying to get her in the hallways of this compound. And the velociraptor learns how to open the door. It's just an incredible scene. That's a great movie. Anyway, that's kind of what I feel like right now. These little velociraptors are attempting to open the door. They'll figure it out eventually. In which case, I'm doomed. But we'll see if we can finish the lesson before then. Okay. So as a first assumption here, I'm just going to assume that all of the H3O plus or the H3O plus comes from the first reaction above with HCl being converted into H3O plus and Cl minus. So I'm going to say that H3O plus is equal to the concentration of HCl, which is 0.10 molar. Okay. because this is a strong acid, it's going to completely disassociate, and I'm going to get, in my final solution, 0.10 molar from the HCl. Okay. This high ionization, or excuse me, this high H3O plus concentration, okay? This isn't the exact concentration, right? We still have some that come from the formic acid, and we still have some that comes from the autoionization. And it turns out that actually this will even affect the percent ionization of the formic acid itself, okay? So if we have let me just write this out real quick. Right? At high concentrations, remember that percent ionization went down for these species. And also, if you think about this from a perspective of a equilibrium, right? So COOH plus H2O goes to H3O plus HCOO minus. If you think about this from the perspective of an equilibrium, we're adding in a ton more H3O plus, right, into this reaction. So what's going to happen with this reaction? This equilibrium is going to shift left, okay, due to Le Chatelier's principle. Remember, good old Le Chatelier basically tells us that if we add more of the product, this system is going to re-equilibrate. It's going to react to that by shifting itself one way or the other to find a new equilibrium. And that's exactly what's going to happen here. We want to solve for how much ionizes by looking at the base concentration in solution with H3O plus initial at 0.100. And what do I mean by that? Okay, so we have our reaction here. Let's write this as, oh yeah, well, that's okay. So we have, let's actually make an ice table here, okay? And we have HCOOH concentration, right? And we have H3O plus, and we have HCOO concentration. Now, the initial concentration of HCOOH is 0.10 molar, right? We're already getting that from the initial part of the solution, right? We're forming two solutions out of these concentrated acids. However, in this case, we're not going to have zero initial H3O plus concentration like we do normally. We're going to have 0.10 molar initial concentration. And of course, this initial concentration is zero because we haven't reacted any of the undisassociated acid yet. We're going to again what's the word? We're going to use X to show the amount of HCOH that has been depleted. And of course, this is the amount that we gain in both H3O plus and HCOO minus. So we have 0.10 minus X at equilibrium, 0.10 plus X at equilibrium for the H3O plus, and X at for HCOO minus. So we can set this up with a Ka. Ka is equal to, what was the Ka? I think it's 1.8 times 10 to the minus 4, right? 1.8 times 10 to the minus 4 is equal to 0.10 minus X, or plus X, times X over 0.10 minus X, okay? Products over reactants. So since Ka is so small, right, we have 1.8 times 10 to the minus 4. I'm going to go ahead and assume that X is much less than 1 or 0.100. Okay, that means that I can get rid of this guy and I can get rid of that guy. So we end up with 1.8 times 10 to the minus 4 is equal to 0.10 times X over 0.10. Those two cancel out, and we end up with X is equal to Ka which is 1.8 times 10 to the minus 4. Now we need to check the assumption. Check the assumption by looking or comparing x with 0.10. If we have 1.8 times 10 to the minus 4 divided by 0.10 times 100, we end up with, let's see, 0.184%. Okay, this is much less than 5%, so this is a good assumption. Okay, that means that x is equal to 1.8 times 10 to the minus 4. And the amount of H3O plus from formic acid, HCOOH, is equal to x is equal to 1.8 times 10 to the minus 4 molar. Okay, now the total amount, right? Total H3O plus so far is equal to 0.10 molar plus 1.8 times 10 to the minus 4 is equal to 1.00018. Okay, and now using the rules of significant figures, we can only use up to this digit. So this is equal to 0.1, not 1.0. We can only use up to that digit because of our initial starting point. So that means that our H3O plus concentration is equal to 0.10 molar. Now we can also throw in the autoionization of water in here, but of course the Ka for that is even smaller than the Ka for this formic acid. And because of that, we know for sure that we can completely neglect it. It's completely negligible. Okay, so it turns out that the total H3O plus concentration in this solution is completely dominated by the strong acid. Okay, so in the case of a strong acid and a weak acid, you can basically always assume that the strong acid is going to completely dominate the weak acid. Okay, and in the case for two weak acids, what happens when we mix two weak acids together? We have a general rule of thumb. General rule of thumb. If values of Ka are sufficiently different, okay, if they're sufficiently different, let's say by factor of 500. Okay, so if one Ka is at least 500 times that of the other Ka, then you can assume that the stronger acid will dominate. Okay. If the Kas are sufficiently different by a factor of 500, then you can assume that the stronger acid will dominate the H3O plus concentration. If they are not, okay, so let's go back to the if they are. If they're different by a factor of 500, then you can just use the ICE table for the stronger acid to determine the H3O plus, and this will be the H3O plus concentration of the solution. Now, if they're not off by that amount, then you have to use this idea of basically exactly what we did above, right, for the strong acid. So we took the stronger acid, or the strong acid in this case, we calculated the concentration of H3O plus from the strong acid, and then we used that for the initial concentration for the weaker acid. This is exactly what you should do if they don't differ by a factor of 500. and then you can solve for the final H3O plus concentration in that way. Okay, that's basically all that we're going to talk about acids as an introduction. Now we're going to go back to bases. Okay, so we've kind of introduced this idea of acid. We talked about how to quantify it, yada, yada, yada. Let's go back to bases now, and actually that's what we will pick up on next time. So I know you have to wait an entire weekend to learn all about bases, but I think that you can handle it. You can take it. You can be patient through the weekend, and when we come out on the other side on Monday, you will see the glory and the greatness of the bases. All right, that's all from me. Hope you guys have an excellent weekend. Email me if you have any questions or if you just want to chat, whatever. Take care.